Here in Lesson 78, we'll be talking about particle motion. This is very similar to what we've worked with before when we talked about motion due to gravity. Notice here we'll be talking about position, velocity, and acceleration as a particle moves along an x-axis. And just like we had before, we took our position function. If we take the derivative of it, that gives us the velocity function. The derivative of velocity function gives us our acceleration function. And inversely, if we have acceleration function and we integrate, that will give us velocity. Integrate again would give us position. Remember, when we integrate, we'll have to have a specific value that we plug in to help us find c in those different situations. So we're going to do 3 different examples here. The first one, a particle moves along the x-axis according to the acceleration function a of t equals 3t. And then it gives us some specific information. The velocity when t is 0 is -10, and the position when t equals 0 is 6. Find the equation that describes the position of the object as a function of time. So we want to go from acceleration, and we're going to try to find the position function. And then once we have that position function, we'll be able to find the position when t is 2. So what we're going to do is we're going to start with the acceleration function, which is 3t. We want to work our way all the way down to the position function. So first we're going to find velocity. Once we find velocity, we'll find position. To find velocity, we have to integrate. So we're going to integrate a of t to get v of t. The integral is 3/2 t squared plus c. Now we have a situation here about velocity. When t is 0, we know the velocity is -10. So we'll plug in 0 for t, and we'll know the velocity is -10. And so that's what we do here. Solving for that, we quickly see that c is -10, which we can plug that back into our velocity function, and we get this equation right here for velocity. We want to continue going because we want the position function. To find the position function, we take the integral of the velocity function. So here's the position function, kind of the work showing here. Taking the integral, we have 1/3, 3/2 t cubed, so we're integrating this function here, minus 10t, and then we have plus c again. Simplifying the fractions there, the 3's cancel, we get 1/2 t cubed minus 10t plus c. And looking at the directions here, the position when t equals 0 is 6. So we can put 6 in for the position when we put 0 in for t. That quickly tells us that c will end up equaling 6. And we can write our position function. So this is the answer to the first part. It says find the equation that describes the position of the object as a function of time. We just did that. Now we want to find the position when t is 2. Well, that's simple. All we have to do now is plug 2 in for t, and we can get that answer. So figuring out the math here, 2 squared or 2 cubed is 8. This would be -20. Half of 8 is 4. Simplifying there, when you add those together, you get position is -10. That means, so this particle's moving along the x-axis. Here's our origin, 0. At 2 seconds, the position's going to be back at -10. That's all that's saying. Looking at our next example, a particle moves along the x-axis such that the acceleration function is a of t equals -3t, which means it's always decelerating. Its position when the time is 3 is 20. Its velocity when the time is 1 is 5. What's the position when t equals 4? Also, at what time is the particle changing direction? This has a little bit more to it. It makes it a little bit more difficult because it doesn't give us time 0 for these two. It gives us time is 3 and then time is 5, but it's not a big difference. It's just a little bit more algebra or arithmetic. This part here asks us what the position is when t is 4. In order to find that, we're going to have to find the position function. And we'll get to the other question after we do this first part. In order to get the position function, we first need to find the velocity function. Once we know velocity, we can integrate to find the position function. So that's what we're going to work through here. Here's our acceleration function. We're going to integrate to get to the velocity function, which is -3 halves t squared plus c. We need to find this value of c. So what we're going to do is we're going to look at this part. Its velocity at t equals 1 is 5. So we're going to put 1 in for t, and our velocity will be 5. Solving for that, we'll end up adding 3 halves to both sides, which gives us 6.5, or 13 halves, whichever way you want to write it. So c is 6.5, again, or you could write 13 halves, which actually is a little more useful later on. Now that we have velocity, we can integrate that to help us find the position function. So we'll integrate this equation here to give us the position function. I didn't show as much work there, but we integrated velocity. We now have this specific situation that the position is 20 when time is 3, so we're going to put 3 in for t and 20 for our position. Working through that and solving that, we can find c. So here's that cleaned up a little bit. 3 cubed is 27. Half of that is -27 halves, plus 39 halves. 39 and -27 is 12, and it's halves, so that's a 6. Then we obviously see c is going to be equal to 14. And then plugging that back in gives us our position function. So what's the velocity, or what's the position when time is 4? All we're going to do is plug 4 in here for the time into our position function. Simplifying that, 4 cubed is 64. Half of that's negative half of that is -32. Here we can do some canceling. It's going to be 2, so we'd have 26 plus the 14. So there I added the 26 and 14 is 40. This part is -32, which gives us the position at 4 is 8. Again, remember we're on a number line. So here's 0 on our number line. At time is 4, we would be at the position 8. The next question says, the last part, also at what time is the particle changing direction? Changing direction, if a particle is moving back and forth, changing direction, it actually is moving one direction, coming to a stop, and then going the other direction. So when you're looking for changing direction, you're really looking for the velocity equal 0. And so we're going to come to our velocity function, and we're going to set that equal to 0. So we're going to plug 0 in for the velocity, and we'll want to solve for t. We can add 3 halves t squared to both sides. Multiplying by 2/3 will help us solve that. And that would give us 13/3. Take the square root of that, and you would get the square root of 13 over 3, which I obviously didn't put on there. So time would be square root of 13 over 3. You could rationalize the denominator, and that would be square 3 root 13 over 3. And our last example, this time we're given a velocity function. The velocity is 1 over t when t is greater than 0, which just means from that time forward it's not going back in time. Its position is 5 when time is 2. Find the time when the particle is 10 units to the right of the origin. 10 units to the right of the origin. Well, that's telling us a position. So we'll need our position function. To get from velocity to position, we're going to need to integrate. So here's our velocity function. The integral of 1 over t is just going to be the natural log of t plus c. We're given a specific circumstance here. Its position is 5 when t, or time, is 2. So we can put 5 in for the position and 2 in for t, which gives us that. And we're going to leave it in this form. I'm not going to find the decimal right now, so I would just subtract natural log of 2 from both sides. And that's c, 5 minus the natural log of 2. And now we can plug that back in for c, and we get our position function. So that's the position function. We needed that to find this part right here, find the time when the particle is 10 units from the right of the origin, to the right of the origin. And so that's really just finding when the position is 10. So here's our position function. We're going to plug in 10 for our position, and we want to solve for t. Well, we can get these to the other side. So that's subtracting 5 and adding the natural log of 2. Subtracting 5 just gives 10 minus 5 is 5, plus the natural log of 2. We can change that to exponential form. So this is log base e. So we can write that as e to the 5 plus natural log of 2 equals t. And then if you want an approximation for that, since we're dealing with a time, we don't really usually talk in terms of e to a power. You find that that is about 296.8 seconds. So a lot of the same strategies as we had with the, we called them falling body problems, or motion because of gravity.